polarized state. And this is a metallic state at which then you add extra interactions and see what this state does, interactions or moire. Then we argued, we took the moire. So we said the first thing we want to do is add moire. And we got into a little bit of a controversy regarding the data, which I think was solved over some nice hot pot and some dinners. But the issue is to, look at these plots and see some quantization and hopefully experimentally get this resistivity Rxx much lower than it is. Hopefully the experimentalists are working on this. I agree with Chrissy that this is very important. Now, the next thing, we added moire, and we got to the puzzle that the moire only influences one side of the sample because that's where the HBN is aligned. You can clearly see it here plotted in the Moire-Briand zone, the band structure. This band, you can see that it's heavily influenced by Moire because this trash can, which was gapless, has open gaps everywhere. But this band, which is far away from the Moire, is basically still gapless. It looks just like a folding. If I just took the trash can dispersion, which is in the momentum space, which is continuous, and again, updates, and folded it to the Moire-Briand zone, it will look exactly like this. There's tiny gaps here, which you can't see. The gaps are of the order 0.1 million electron volts. And this being away from the Moire, you basically see no gaps. If you were actually to count these tiny single particle gaps, you'd get the wrong Chern number 5, rather than the one that's observed in experiment that's filling one of the Moire unit cell, which is Chern number 1 for value K. Then we said very briefly that you could form a solution, which is a Wigner crystal solution in Hartree-Fock, in which you basically take this trash can, model it as a hexagon, because you know that triangular lattice is more stable in Wigner's, most one, and make a translational symmetry breaking at this vector that's related by KB to KB, basically twice KB, etc., something like this. So you can make this translational symmetry breaking. These regions here, you fold them, and you can get a Hartree-Fock state. And this Hartree-Fock state, you can then show analytically. So the Harvard and MIT groups and the Flatiron groups basically showed analytically that the Chern number is 1 mod 3. But with the trash can model, you can show that the Chern number is actually 1, not 1 mod 3. And it, after Hartree-Fock, the Chern number matches, its sign matches the flux of the Berry curvature inside the bottom of the trash can. So the ferromagnetic coupling is not Chern number -1, is 1 if the Berry flux was positive, and minus if it was negative. Then we argued that this solution has problems, or you'd expect it to have Hartree-Fock solution, you expect them to have problems. The reason for this is that we know already Hartree-Fock has problems on things that look parabolic, on, gallium arsenide, just pure gallium arsenide with parabolic dispersion. And Hartree-Fock only takes into account fluctuations around the Fermi surface, but in these type of trash can problems with a flat bottom, the fluctuations certainly are not just around the Fermi surface, because it costs as much kinetic energy to excite from here to here as it costs from here to here. So you have a large region of fluctuations that you expect the Hartree-Fock to be unstable. Then we basically showed results, and these are results from these groups, also from us. I would encourage you to look at Sid's Journal Club commentary on this, which is a commentary of this early on before these issues sort of got solved, mainly, as they get solved by experiments. But we pointed them out in this paper by Ifwan and Jabin Yu and other people. Basically, the moral of the story is you do a Hartree-Fock. They were also pointed out, by the way, by Jampeng Yu and some papers by Yangbak Kim and Shankar and other people more recently after this. But basically, this is the dispersion with small Moire gap. You can see the small Moire gaps of the conduction band. So you can think of this as basically gapless. This is dispersion after Hartree-Fock. you see single particle dispersion. So this is the charge sector. You see a large gap and a flat band of churn number 1. Now, then the story continued. So this was supposed to be the integer churn state without moire, a Wigner crystal with a phonon that is gapless. Okay, and then if you take this and partially fill this band, this churn band, then you're supposed to see, because it's a churn 1 band, so basically you can think of it as a quantum Hall state, and you see at filling, say, 2/3, you see a 3-fold degenerate ground state, okay, which is, if you weed out charge density waves by some other methods, it's a fractional churn insulated ground state or a fractional quantum Hall state on without a magnetic field. So, questions so far? No questions? Everybody's just barely awake. Okay, good. So the moral of the story is, you could say that that's the end of the story, but if you really want to obtain things from first principles, there's massive problems with this type of argument. And the problem is the following. The problems are basically the following. The band structure, the charge excitation band structure of the Hartree-Fock that you've obtained after Hartree-Fock looks like this. But in Hartree-Fock, this gap, the Wigner crystal gap, the charge gap of the Wigner crystal, I'm not plotting the neutral spectrum, which will show the gapless phonon, but the charge gap of the Wigner crystal is basically a fraction of the interaction, because you put in the interaction, and when you do Hartree-Fock, everything is dependent basically on the interaction. This is a fraction of the interaction. But if I then project to this band and add the same interaction to get the fractional churn insulator, that misses the fact that I'm adding the same interaction that created this gap. Okay? So this interaction that created this gap is larger than the gap, obviously, and then you're going to have strong band mixing. This is much stronger than the quantum Hall effect, where you can just tune the band mixing by increasing the magnetic field. Right? You separate the Landau level gap, the cyclotron gap, and then you weed out band mixing. Here, in this scenario, the band gap is given by the interactions, and you have strong band mixing. This is the same statement as saying you should start from the very beginning, where you have a gapless band structure, and then go to the correct filling from the very beginning without doing Hartree-Fock, and then obtain the state, or try to obtain the state in an unbiased calculation. Now, unfortunately, doing that is not easy, at least certainly theoretically. We don't yet know how to deal with this fully theoretically. I'll show you some exact solutions later, hopefully if I get to it, of the Berry trash can. But numerically, which is how you obtain states in fractional quantum Hall effect almost exclusively at the beginning, then of course you get this nice composite fermion picture, but Jan Andrei also did numerics to confirm that it works. So basically, numerics is quite important. In this case, numerics is very hard because you have many bands. The reason is that if you want to start, for example, from this trash can with small gaps in the moire, you basically have, for example, at the K point, these are small moire gaps. At the K point, you get 3 bands that are basically degenerate when you fold to the K point. So you have at least a 3-band problem, and doing 3 bands is very expensive numerically. And it's a gapless system, you're not going to get very far. So what we do is we make a scheme where you can introduce fluctuations, i.e. matrix elements to other bands, progressively. So what we do is we first take this Hartree-Fock band, and this is just called band projection. This is the Hilbert space of the band projection. You can partially fill it and work in the Hilbert space of this partially filled band. But then you successively add the other bands by letting particles move from this band to the other band. And when you do this, you cannot do this fully because that's too expensive. Hilbert space grows exponential. But when you do this, what you do is you focus on regions in the K space that are important. So for example, I'm not going to allow particles to go here because that's kinetically forbidden. So I'm going to focus, we're going to focus, or, Jabin, Nicolas, Yves, etc., focus on regions that are very close to the gapless points. And then you also don't let all the particles, you don't allow a Hilbert space where you move, where you allow all the particles in this band to move here, because if I move all the particles, I would also have them kinetically forbidden, even if they're close to these former gapless points, which are now separated by the Hartree-Fock gap. So you just allow more and more particles, and this adds more and more fluctuation. Is it clear what we do numerically? And then you diagonalize the interacting Hamiltonian in that Hilbert space. Now, which interacting Hamiltonian diagonalize is very, very important, and this is what you get. So if you just project to the flat band, to the Hartree-Fock band, that's basically neglecting the fluctuations that I argue are very important. You get three states, FCI, 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 FCI. But you now add fluctuations successively, and this is how it looks. This is just this plot, basically, no fluctuations. 0, 0 means fluctuations in the first band and fluctuations in the second band. Remember, at the K point, without Hartree-Fock, they're all threefold degenerate because they fold there on the Moiré scale, even without the Moiré. If I just fold them to the lattice size of the Moiré, they would fold. I would get threefold degeneracy at that point. So you have three band. This gives you the number of fluctuations, number of particles allowed in the first band and the second band. And just allowing number of particles in the first band, you see the gap of these three states, FCI states, collapsing, and the ground state going to different momentum sectors. These momentum sectors, I don't have time to explain, but they're related by a very, at the beginning, they were, you can just fold the fractional quantum Hall states into these momentas and find that these are the momentas of the SCI. But then there's Lieb, Matte, Schulz more recently theorems that basically showed that there cannot be a gap state at these momentas, and there cannot be an FCI state at these momentas. The FCI states need to be at these momenta. So you can see that the effect of fluctuations collapses the gap, and you don't get a fractional churn this way. Questions? Yes? These ones? These ones is the number of particles you allow in the next band. So you form the Hilbert space with just the Hartree-Fock band, which is isolated, but then you allow fluctuations in the other band because the interaction is larger than the Hartree-Fock gap. That's always going to be the case because the Hartree-Fock gap came from the interaction. Or in the same language, you can just start from the gapless point at the beginning, not do Hartree-Fock, and allow fluctuations in the other band. And these are the numbers. So you see, you don't even need to go to the next band to see the gap collapsing. Yeah, so you take window, roughly the Coulomb size. Very good.
But that's similar to MagLab.
Exactly. But they're worse than lambda level mixing because the system you start off with gapless. So they are exactly like lambda level mixing, but if you thought about lambda levels are like this, but this system is like this.
Yeah, so I also expected this to be much more sticker lambda level is done a chain called
Right.
Different trend state. They not only in the planet but having imaginary like that.
Exactly. So you don't right. So you basically don't. So certainly So this is the loss of the fractional Cauchy effect, but you lose also the Chern insulator state if you add. You lose even the integer state if you add this fluctuation. Very good. Without Moiré. So this is all without Moiré. But I've argued that Moiré is weak. So how do we change the problem? So the root of the problem is that the Wigner crystal is unstable, actually. And this was seen early from time-dependent Hartree-Fock calculations. For example, this is Yves and Jabin's calculation at the beginning. This is the time-dependent Hartree-Fock spectrum. Now, I'm not arguing the time-dependent Hartree-Fock is correct, but it's certainly better than just Hartree-Fock. So you look at the Hartree-Fock spectrum, you see there's a small gap here in the phonon because you have a Moiré. We did put a Moiré, but so we, otherwise this phonon would just go to zero. There will be the Moiré effect is tiny, but is there. Even on the conduction band, as I had argued, is very tiny. But, I could do the same calculation at zero Moiré and get the same charge band, but then the collective mode would go to zero. But you can see the collective mode has massive amount of unstable modes. Now, I don't have proof of this in analytically, but this is one of the things that we're currently doing with this, or currently starting to do. But if anybody wants to do it with a Berry trashcan model, because it's analytical, you might be able to actually do the time-dependent Hartree-Fock analytically and find out why it always seems without moire to be unstable. Okay? So there's a reason, there's a deeper reason for this, at least in time-dependent Hartree-Fock, which hopefully you can do analytically. Okay? So the first thing that we said is how to stabilize the Hartree-Fock state in time-dependent Hartree-Fock. And there are several things. This is the gap of the collective mode. The gap of the collective mode is basically the moire, because it's the phonon collective mode. Because if I didn't have, if I had a really Wigner crystal, this gap would be 0. So there's several options for this gap. The U is the interaction. This is the first option, that this gap would be larger than interaction. This is nonsense. It can never be this, because the moire is not large enough, because the side is away from the moire. So this never the option. This is what we get. This is what basically, the modes are unstable, the collective modes. But what we really want to is to at least first get this Hartree-Fock state stable in time-dependent Hartree-Fock. Now, it turns out you cannot do this without moire, as I don't have time to show you. But you can do this with moire, but then you have to explain how the moire, which is strongest on the bottom, affects the top, which is where the conduction band is. Okay? And basically, this, I don't have really full time to go through this, but this is the moire capacitor effect that basically tells you that the single particle Hamiltonian doesn't have any effect on the conduction band. But if you add the single particle Hamiltonian plus the Coulomb effect, the Hartree terms of the valence bands, then you do have an effect on the conduction band, as I'll show later. So this actually requires a good analysis of the Coulomb interaction within these layers. The Coulomb interaction, first of all, is not just the Coulomb interaction. It gets screened, it gets some contribution from the valence band, as I'll show later. So how you treat the Coulomb interaction and the subtraction scheme in these layers is very important, and I would urge you to look at Ciprian's papers for analysis of these 3D multi-layer Coulomb interaction. These are the type of interaction basically that we use for this type of calculation. So now, what do we do? So, in a nutshell, this is the prescription. So, the interacting Hamiltonian is basically taken to be normal ordered with respect to the charge neutrality point. This is the charge neutrality point before, so this is, this is the band structure with moire. You can see the Berry trashcan folded here. No, this is the single particle band structure. No gaps. This is the valence band. You can see the gaps opened by the moire here. And this is delta of the density is the density minus 1/2. Okay? And minus 1/2 in density normal order with respect to the charge neutrality, for example, is the same scheme that Oscar and other people use in twisted bilayer graphene. If I was exactly without a displacement field, it would be normal order with respect to this point. I had a rho minus 1/2. So delta rho is rho minus 1/2. Delta Q0, rho of Q minus 1/2 delta Q0. But because your low energy Hilbert space is just the conduction band electrons on the filled valence band, this filled valence band, and 80% of it is actually just coming from the first valence band, feels the effect of the moire through a moire term in this density interactions. So it's a Coulomb effect that this density interaction, which you take rho of Q, you sum over all the Q's, okay, including the moire Q, because the Hilbert space is actually C of the conduction band, not on the vacuum, but on the filled valence states, then you're going to get a contribution at exactly the wave vector of the moire due to the valence band. And that's basically a Hartree contribution. You get a Fock contribution, but that contribution just renormalizes some velocities. And the Hartree contribution does this. So this is how the density of the valence band looks. Okay? The density of the valence band, because it's close to the moire, has these big gaps. Okay? It basically mimics the moire. And this valence band, by the way, is actually a Chern number 0 band. They can build a Vanier description of this band. You don't have any obstruction. You can build a Vanier description. Is very localized, actually, orbitals, and it looks like a triangular lattice given purely by the moire. Through the Coulomb interaction, this now hybridizes with the conduction bands purely through the Coulomb interaction. And, you can do some, using, for example, Cyprian's Coulomb interaction, you can do some perturbation theory, and you see that you get a contribution from the Coulomb interaction. This is not it becomes a single particle contribution, but it doesn't start from the single particle model. It's only through the presence of Coulomb effect. You get a contribution to the conduction band, which is proportional to this. This is the moire potential. So this is how it changes the band structure. From a band structure that started off as being gapless almost, very tiny gaps, now you have large gaps at the K moire points, okay? In particular, the third band here has moved way up, and this is an important moire effect. And this moire effect is only due to the Coulomb interaction with the valence bands. Now, if I was to just compute the Chern number of this band, this is the Hartree effect. You can restate this as a single particle Hamiltonian, and you can compute the Chern number of this band. This Chern number will give you -1, so it's still the wrong Chern number. Okay, so it's still, the state is still not a non-interacting state just with the moire. Even the Chern insulator state, that filling 1, is not a non-interacting state because it would be the wrong Chern number. But because of this effect, you now stabilize the state at Chern equals 1. Why? Because you can think effectively that the state at Chern equals 1, even without moire, has some triangular form. Okay, with moire, the valence band looks also triangular. When you put the Coulomb in between the valence band and the Chern 1, you can see that the whole electron attraction, and that stabilizes the lattice and makes the collective modes at Chern at filling 1 non-negative. Okay, so questions with this? There's got to be some questions because I went a little bit fast. Is it clear what we do roughly? Maybe not. So again, this is the Hartree term from the valence bands obtained from the Coulomb interaction. This valence band rho really contains a lot of moire because it's close to the moire site. Its density looks like this, okay? And this density locks in the fact that this has a moire form through the Hartree term, locks in the density of the Chern 1 Hartree-Fock band at filling 1. Okay? Yes?
It's interesting, like, it's so that Hartree-Fock is here.
So, yeah, so it depends which Hamiltonian you start off with. If you neglect the Coulomb interaction between the valence bands and the conduction band, i.e. if you just do projection to the conduction band, we'll never get this, even if you implement Hartree so consistently. So we tried, I can't say you'll never get it, but I can say we tried for 2 years and never got it. They never got the Hartree-Fock, fully stable. And moreover, the exact diagonalization, which is really exact to work out. So basically, it's not an effect of just implementing the Hartree-Fock so consistently on the, Wigner crystal Hamiltonian without the moire. That you won't get this. So hopefully the plan now is to understand it from this trashcan model where you can do things analytically, and to understand the time-dependent haptic fork analytically, and understand why it's not stable. Or at least what we've tried is not, maybe we find a regime in which it is stable, and then we can maybe look at that regime in the exact analyzation. But so far, we haven't been able to find a regime. But of course, if you have many parameters, once you add extra things, it's hard to tune all these parameters and do exact diagonalization calculations. So what you want to do is to use some analytics to find a sweet spot. And but so far, as I said, with numerics, we haven't been able to do it without adding the moire. So when you add the moire, then if you add it in a single particle, meaning, just terms, you just add the hoppings to the, from AGBN to the, and then you twist them, that opens tiny gaps. If you don't add this Coulomb term, you can again never stabilize. But if you add the Coulomb term only in this ordering, rho minus 1/2, we tried, other orderings, doesn't work. In this ordering, with this ordering, you can get, as I'll show you on the next slide, both time-dependent haptic fork that's stable, and then once you find the sweet spot of that fractional translator region that's stable. Now, this is no longer a Wigner crystal because the effect is a moire effect that comes from the coupling through the valence band. It's just that the coupling, the coupling is the single particle term now. It's a Hartree term that comes from the interaction of the conduction band with this valence band with the strong moire. Does that make sense?
Yeah.
Can you speak a bit louder? I'm old. Yeah, I see what you mean. So you want basically to do Hartree fork on more than on not just. So that doesn't change very much the valence band. The reason why that doesn't change the valence band is the valence band is basically, so you can think of this as some sort of a heavy fermion, a system where the valence band is really heavy because the valence band, we see these gaps, okay, they're not huge, but they're 10, 15 milli-electron volts at every direct gap of the valence band. This band has Chern number 0, so really you can vanierize it. And you see 85% of this density that I'm going to show you that I plot here, so comes from just that band, from the Hartree of that band. Now there's some Fock term issues that diverge, etc., but the Fock term actually all that it gives you is some renormalization of the velocity. That's what we argue. To do this calculation correctly, you need to do, up to the bandwidth of graphene, etc., but to do it fully correctly. But basically, this, for us is good enough. 85% of this type of density comes from just the first band, which is a localized band of orbitals due to, some collective orbitals due to the moire. It doesn't change if you do Hartree focus with including these bands. That doesn't change very much. Yeah. So in the Hartree, there's no, but in the Fock, there's some, this is an old problem in graphing that, so that's why if you really want to do correct calculation, you just do it up to the bandwidth of graphene, etc. What we argue is the Fock term just gives you some renormalization of the velocities and we use the velocities in the experiments of the graphene, which are about 20% different from the ab initio velocities. But that's how we deal with it.
Good. Actually, I think you say something. Go back to this. Talks about four. This would appear like you even. Let's see where anything to with that. The only thing that authority doesn't change you talk about it.
Exactly. The rho valence has different Q vectors, right? Because in the Coulomb you get rho Q, rho minus Q. But rho Q, the the Hilbert space is not C dagger of the conduction band on empty, it's C dagger on the valence band. So then in the rho Q, in the summation, you're going to get summations from rho of G. Okay? But that rho of G, on the conduction band doesn't have much effect because it don't have the more, but on the valence band it does. So that's the term that you're going to pick up. Very good question. Okay, so now this is the result. So the way we hunt this is a large parameter space. So the way we hunt is that in this prescription of, with the Moiré term from the valence band, we look for when you get the largest stability in the density and the Moiré-Hartree potential in D field at filling, for example, 2/3, where you get the largest stability of the Hartree-Fock solution. And the way we account for the filling, is a bit ad hoc by just multiplying the bandwidth of the Hartree band at filling 1. But it doesn't matter. Let's forget about that. So you can do the same thing at filling 1 and the diagonalization. But so basically, this is roughly the region where the time-dependent Hartree-Fock with the Moiré potential gives you the largest stability, the largest gap in the collective mode also. So you focus here, and now you redo the scheme with adding fluctuations for these parameters. So, there's a lot of parameters. These calculations with adding fluctuations take a long time because you have 3-band. Basically, you're trying to do 3-band calculations almost by progressively adding fluctuations. So you need to really focus on some region of stability. And this is the first time we have been able to basically stabilize so this is the plot that I wanted to show you. I don't think it's not published yet, but basically the moral of the story is the following. 0 just represents projection to the Hartree-Fock band. So no fluctuations added. Okay? This is fluctuations into the second band, and this number is the fluctuations into the third band. Okay? Because I argued that for just the Berry trashcan, if I fold it, I would have a 3-fold degenerate point at K. So I need to take into account 3 bands. So this is what we do. So notice that in this region, the FCI gap at just Hartree-Fock, no projection, so no fluctuations in the other band, is tiny. You can see the Hartree-Fock gap here. Okay? Now you add fluctuations in the second band, and the gap grows. Okay? You can clearly see it. There's a number of particles that you allow successively in the Hilbert space to reach the second band. Okay? So you can see that basically band mixing traces the FCI here. So at the beginning, we were actually looking at this region, and we thought, this is great. But then when we added the third band in this region, actually it turns out that the gap collapses. But then we just basically saw that there's a clear region. And here's what happens when you add fluctuations into the third band. The third band are these. So this is fluctuation of second band, third band. And you can see the system basically saturating and the FCI gap not collapsing. So you see, basically, there's two morals of the story. The band mixing, at least in this type of situation, in which this is the only situation we were able to stabilize an FCI state, strengthens the FCI. That's point number 1. And point number 2, that in this is the largest size we are able to do, which is 4 fluctuations to band 2, 5 fluctuations into band 3. You can have other sizes, 6 fluctuations to band 2, 2 fluctuations in the band 3, etc. But you can kind of see, well, at least I'm getting to be a little bit satisfied with the fact that you can saturate at a larger FCI gap than what you started off with. So the band mixing in this case strengthens the FCI. We don't understand this analytically. Second thing that you can say is you can plot the density matrix of this FCI and show that it's not just a single band FCI. So it doesn't appear, well, it's probably obvious from here, it doesn't appear, whatever rotation you do in the subspace of bands, you cannot never express it just in terms of a one-band FCI. For example, there's about 30% mixture of bands in this fractional Chern insulator. Okay, so with that, I wanted to end the fractional Chern insulator side. Any questions? Yes.
How about it? You know, what state if I'm on the island, or
They do. They do. I don't have. They do, and they will. And I don't know how they do. I don't even know if we can really get them because these calculations are very expensive. So we don't have a swap. So these are done for epsilon equals 6, 5, something like that. But basically, they will change. So the idea would be to understand this type of regions analytically and understand roughly where you get the largest stability for time-dependent Hartree-Fock analytically and why we don't seem to be able to get it without Moiré. And then we can go to other things. But they do change with the... Any more questions?
yeah, like this to go some moment and start on some point. So it went to come, but I wouldn't. It'll be in touch. You may get a lot of the street.
Oh,
Actually, gas and you are still in the cat.
I see.
And that ain't it.
I see.
That's it for me more. I don't think that I'm going to see all the help that stuff. And I'm like, I think after that, maybe just have some making them uncovered stories.
I see. This is very interesting. I wasn't aware. But yeah, I mean, if we were able to do some perturbation with this gapless band, some perturbation here where we show the same thing, that would be amazing. Yes. Okay. More questions? We do it right. No, so here, right. So here the AD is done with the bands that you get with the Hartree term of the Moiré. If you did it without the Hartree term of the Moiré, everything would collapse. So that was the paper that Jabin had like that bust a year and a half ago, 3 years ago. If you do it, if you do it without the bands of the Moiré, everything collapses. There's they just go to all to zero. So this is with the Moiré, and you do ED on that Hamiltonian with the Hartree terms, with the Hartree term of the Moiré, with the baneless band.
Do you want that into like to get the study accounts and you trying to do?
Oh, you don't do the. So once you've taken care of the baneless band, you don't go to the baneless band anymore. That will be way too expensive. All these 3 bands are just the conduction bands, and the baneless bands have been taken into account by this Hartree term. Otherwise, it will be prohibitive. Okay, more questions? Okay, so then this is basically the region of stability of the FCI. So after 2 years of work, we are able to get some stable FCI at sitting 2/3. Now, the ratios that are seen in the experiment go all over the place. So 2/5, etc. So I think there's a lot more work to be done to fully understand this, even just in time dependent Hartree-Fock analytically for example, Chern equals 1. But now I wanted to basically go to the superconducting side, and again, a point taken from Bridges' point yesterday that this superconducting region, we still need to figure out if this is hundreds of ohms, maybe not hundreds of ohms, but tens of ohms or really zero. But in these samples, when in this superconducting region, where this is the exact or similar density and displacement field as the FCI state, superconductivity has been reported in the MIT paper. Now, this region, as I argued, is the same as this bottom. Now, I don't know what gives you superconductivity, i.e. what gives you the attraction in this case. I'll have something on the last slide if I get to it. So this, I don't know. But what we can ask is, if we put an attraction by hand, what do we get? And of course, you can say, well, if you put an attraction by hand, is very obvious that you might get superconductivity, and I can tell you yes, but it's not obvious which type of superconductivity you get. You can get, since this is a single flavor system, you're going to get it to be odd in momentum, but it's not clear if you get kx, ky, kx plus iky, kx minus iky, kx plus iky cube, kx minus iky cube, etc. So this is what I wanted to show you, that in some limits of this problem, there's an exact solution that tells you you always get kx plus iky. So what does that mean? Remember that I said that at value k, the Berry curvature of the bottom of the trash can is positive, and also the Chern number of the FCI state, or the CI state, etc., is also positive. So it's a ferromagnetic coupling of the Chern number with the bottom of the trash can. Same thing happens in the superconductor. The chirality of the superconductor ferromagnetically couples to the Berry potential, to the Berry curvature of the bottom of the trash can. Okay, so this, yes. Yes, exactly. So this is 2K. So this is Berry. So this is all quarter metal. We assume everything is fully valley and spin polarized. So then what you get is so pairing around here is pairing K to minus K here, or K to minus K here, as you'll see, but it's a 2 big K pairing. So it's got a paired density wave. Well, I mean, you can, I can make maybe form different combinations of this K, but it certainly has some component at this K. But it's within, and I think, I mean, the evidence for that, depends how you want to look at it, but certainly there's an anomalous hole in the parent state. So, it breaks time reversal, etc. And it's in the same region as the FCI, which basically has to be, or CI, when I put moire, which has to be valley and spin polarized. Okay, so what's the solution that we can solve exactly? Instead of putting these trash can walls to have the Dirac velocity, we put them to be infinite. Okay, now that's an approximation, obviously, but the hope is that since the Dirac velocity is so large, this is, these excitations here are kinetically forbidden, so it's not so bad. We'll see if it's not so bad or if it's bad. And then you just solve this Hamiltonian with the GMP form factors. When alpha equals to beta is exactly the GMP form factors. We did alpha not equal to beta, which corresponds to some V of Q, which is not contact interaction. When alpha equals to beta, V of Q is exactly contact interaction, and the form factors are exactly the GMP algebras. And you do it at a density, from 0 to pi times kb squared. When it's exactly pi times kb squared, of course, since these walls are infinite, I just have one ground state, which is just filling up this thing. That's not a superconductor, but you also see that the superconductivity dies when you get to pi kb squared. So, roughly. Okay, so this is the model we're going to solve, and I don't have real tons of time to go through it, but the moral of the story is that model you can solve exactly in certain cases. For example, the two-particle solution can be solved exactly of this model with V of Q negative contact interaction. So V of Q, alpha equals to beta, these are form factors, alpha equals to beta, V of Q negative U less than 0. Then these become the exact two-body solutions, okay? K plus e to the minus beta, this is alpha equals to beta in this case. Beta is Vf squared over T squared, T perpendicular squared, gamma K dagger gamma minus K, okay? At momentum is 0 within the trash can. Of course, everything has momentum 2K. Here is this K, big K plus K, big K minus delta K. And the lowest two-body energy is M equals 1. Okay? So this is an exact statement. So now we can ask what's the ansatz for more electrons. So let's just take in this two-body operator, which you can see it's a Cooper. Well, obviously it's a two-body operator, so at momentum 0, so it's a Cooper pair. But the question is, if I start putting more of these Cooper pairs, do they condense? And we're going to do the ansatz. You can just focus on the even number of electrons. This ansatz works quite well. And you can do this ansatz as taking this operator to the nth power. And this operator is K plus IK or P plus IP superconductivity. Is the ground state for two particles. And the reason why it's the ground state is the same thing. The Berry curvature of the Berry trash can selects the chirality of this mode, selects that m equals 1 rather than n equals -1 or other ones at the constant. Okay? So we're just going to take this operator and ask what's the what happens if you condense. That operator is part of a larger set of operators called RQ, which are momentum Q within, this is Q, all of this happens within the trash can. Momentum Q pairs, and RQ is K minus gamma Q minus K. This is a momentum Q operator, gamma K. That operator before, was R at momentum 0. Remember K, well, O dagger, if this is K minus, the other one is K plus, is R0 at momentum 0, gamma minus K, gamma K. So now I want to point out the following fact. This alpha or beta times KB squared is a number less than 1. Okay? It's usually around 0.3. Okay? If this factor is then approximated by 1 minus alpha, if you do a linear approximation, 1 minus beta Q squared minus IB, because this number can basically be only as high as beta KB squared, which is around 0.3. So if you do the linear approximation of this Gervin-Klassen-McDonald factor, then this Hamiltonian has the BCS, the pairing ground state that I wrote here as an exact ground state for any number of n. Okay? So, to make a long story short, in the linear approximation in beta, it's in the theorem alpha and beta, it's the same thing here, that I take them to be equal. There, it's Gf squared over Q squared. The interacting Hamiltonian is a negative semi-definite Hamiltonian because U is negative, and it has this form, RQ dagger RQ, where RQ is this guy. Okay? Now, this brings some story from Scar and from, eta pairing, but basically, the moral of the story is the following. This operator, O2, which is the R operated Q equals 0, is just a Cooper pair. O2 dagger is K plus gamma minus K dagger gamma K. This is the Cooper pair at momentum 0 within the trash can. K plus IK Cooper pair. This operator does not commute with this Hamiltonian. You can just do it. You can just do the commutation. It does not commute with it. But when you act it on the vacuum, it does commute. So this is the following exact statement. And it commutes up to some energy E2, which is some, energy dependent. It's basically this constant. Okay? So it doesn't commute with the Hamiltonian. If it commuted up to this energy E2, then you'd have a spectrum generating algebras. All the states would be, would come in multiply separated by E2. But it doesn't commute. It only commutes when added to the vacuum. Okay? So this is the correct statement. But then the second order commutator commutes. Okay? So this is 0. So these two things are enough by simple algebra to tell you that O2 dagger to the power n times the vacuum is an eigenstate, and some simple negative semi-definiteness counting will tell you this is the ground state. Okay, so this is the ground state of this Hamiltonian when alpha or beta KB squared is smaller than 0.3, where you can do the linear approximation. This is an exact ground state. And it's due to this spectrum, restricted spectrum generating algebra, where you don't have the commutator being zero, you don't have the commutator being equal to some energy times the operator, but you have it when acting on the vacuum, and the second order commutator vanishes. All these are enough to prove that. But now what you can do is you can say, well, you didn't have a linear Hamiltonian, you already had the other Hamiltonian. So what we do is we use this ansatz and we do exact diagonalization or overlap of this ansatz, which is O2 to the n number of particles, versus the exact ground state. Don't look at the odd number of particles. We don't have a good ansatz for that's the volume of excitation. We don't have a good ansatz for that. But look at the even number of particles. The overlap is 1. So this is a good ground state, I would say, or close to 1. Good ground state even for finite, for the non-linearized Hamiltonian. You can see the binding energies. You see the even odd effect of the binding energies. Of course, when I fill up the entire trash can, since the walls are infinite, I get to 0 binding energy because there's just one ground state. But for everything else, the binding energies are finite, and it will say the off-diagonal long-range order of the system. This is the eigenvalue of this operator, which has a finite value in the thermodynamic limit. So with that, I hope to have convinced you that at least if you put, we don't know where the attraction comes from, but if you put a negative attraction, a negative U on the model short-range attraction, then the superconductivity in this model has to be K plus IK, Ks plus IKY. Now, if this model is correct, and there's many things to argue here, whether this model is correct or not. For example, there could be pocket physics. This could, extra terms might make this dispersion being a Mexican hat. It might be that the superconductivity is seen in that regime. So there's many things to argue that this model is not correct. But if this is correct, then I would say Luttinger-Kohn is not favored because you don't have any Fermi, you don't have any KFs in the density below here. As there's only two things that can get you attraction, spin fluctuations, because this is a ferromagnetically ordered state, or phonons. Okay? So these things that we computed, for example, both the spin fluctuations and the phonons, in preliminary, phonons are not, obviously, they don't overcome Coulomb. The question is how to overcome Coulomb here. And for that, I don't have an answer. But what I do have to tell you is that if you solve the same trash can model with positive interaction, i.e. Coulomb interaction, you get a ground state which has a lot of degeneracy. And in some cases, you can also solve it exactly in that case. And then maybe these degeneracy phonons can act in the space. So the ground state is not in, you have a large degeneracy, phonons can act in the space and get attraction in this space. But, that the jury is still out on that. There's other things to compute here, such as superfluid weight, which we're currently doing. So these are some future directions, and I wanted to close, and I think I'm closing on time. The future directions that I think would be nice to do is to get an analytic understanding of the Moiré potential on the simple Hamiltonian and the extra terms, especially why it doesn't seem to show, stable non-Moiré time-dependent Hartree-Fock solutions. Then to basically obtain these collected modes analytically, and to get phonons and spin fluctuations. Then try to see if you can get superconductivity by adding both phonons and Coulomb interaction. And the idea would be that first you solve the Coulomb interaction, you get this degenerate low energy subspace, and then in that subspace you add phonons which certainly have lower energy scale than the Coulomb. So that would be the next step for this. So with that, I want to thank you for your attention and take some questions.
We're going to take Friday, I guess we have possibility and 30% of the given person will be after that, but under 30. Anything else?
Which is
Or further. Hey,
Yes, so it turns out, this is unpublished, turns out that this model, again, if you put repulsive interaction, they take this model, you diagonalize it, and then you see that both the high, with whatever you want, not contact, but those, screened Coulomb, highly screened Coulomb, you see that you can find the exact states at both the ground state and the highest excited state, whatever the interaction we get will mix. Now, with positive interactions, there's a low energy manifold of states with positive interaction that up to some filling is exactly degenerate in some limits and highly degenerate away from that limit. It's still, it's exactly degenerate in some limit and a little bit, the degeneracy splits away from the limit. So you can get exact solutions in some limit, just like here. Now, those exact solutions we haven't fully obtained them, but you can clearly see that the energy becomes zero by computer. But you can clearly see that there's and you can clearly see that there's thermodynamic or some densities, number of them. So then the idea, and then you get some higher energy. So then the idea would be that, these other pairing mechanisms like phonons, etc., would act in this Hilbert space. But that's just a hope.